Integration by parts, essentially when you look to use this, it's because regular U substitution is just not going to work. The expression that you are given is just too complicated. It usually has multiple polynomials in it, and so in order to do anything with it, you have to do pieces at a time, and that's what integration by parts is. This is on page 146. Okay, this is the formula that you're going to be using for integration by parts. So this is your original problem. Here's the problem given. I wish they wouldn't use U, but they do, just because we use U substitution. It's a different U, but we are still going to use U as something to substitute with. But in order to integrate this, first we're going to multiply U and V together, then we're going to subtract the integral of V du. This you need to know, UV minus integral of V du. And what's going to happen is you're going to have to identify from the expression which one you want to be U and which one you want to be dV, because we're going to end up using those to find V and du. Okay, so notice V's in two spots, but I have a U and a du. Okay, and this is what's in the book too. It's very small, but it's just some idea. Okay, and I mentioned this the other day, the last line. Basically, what you're going to do is you're going to let U be the part whose derivative is quote unquote simpler. And I say, and it's in quotations because that doesn't mean it's going to be simple. And that's why in parentheses it says, or at least no more complicated than U itself. Okay. Then you're going to let dV be the more complicated part, or the part that's going to be integrated, because we have to find V. And in order to get rid of the D in front of the V, we have to integrate. Okay. And you typically are going to have two choices. You're going to have one option for U and one option for dV. Here's the trick. If one choice doesn't work, try the other. So these are problems where you think, maybe I figured out what U should be and what dV should be, and then you start working through it, and all of a sudden you go, oh crap, this is not going to work. And so you have to stop and start over and switch it up. When we get into more complicated forms of integration, that will happen. Okay, and so just be persistent, and eventually you'll get there. But that's what you have to know about complicated forms. Complicated integration techniques. Sometimes it doesn't work on the first try. Don't be surprised if that happens to you. All right, let's look at an example. First example doesn't look too awful. And keep in mind, if you can do regular U substitution, you should try. And you should consider regular U substitution right from the get-go and decide, okay, if I make U x, does that help me at all? If I make U e to the x, does that help me at all? And you just have to consider what their derivatives are, right? Like, obviously, the derivative of x is 1. That's not really helpful. The derivative of e to the x is e to the x, so that doesn't take care of the x. So that's where you can right away go, after you've done that analysis, U substitution is not going to work. And so right away, your really only option, since I don't have any fractions here, we don't have to deal with any of the stuff that we did in 6.5, is integration by parts. And so for this first one, okay, what we're gonna use, so here's where that idea of simpler comes in. It's either x is going to be U or e to the x is going to be U. Okay. Which derivative is simpler? Is the derivative of x simpler than the derivative of e to the x? I think that's a matter of opinion, right? They're both easy. But when I take the derivative of x, I just get a constant, 1, which if we were to really get into an arm wrestling match about, I think we would say 1 is simpler than e to the x. Yeah? So let's say that u equals x, And then everything else equals dv. Okay, so u equals x, and then everything else has to equal dv. So we have two parts that we need. Okay. We've got u, that's going to be in play right here. This is eventually going to be v, because that's the rest of what I need. But I also need du. So I need v and I need du. That's always going to be the case. So we're going to take the derivative of this side. This is why they talk about taking the u be the derivative part, because we're going to take the derivative of this, and then we're going to integrate this. Okay. So what is the derivative of this? Yeah, it's du. Okay. And then I'm going to integrate this one. Okay. And so obviously this is just e to the x. And we're not worried about the constants and plus c or anything like that. Okay. So now I have all the parts, and now it's just a matter of substituting back into the formula. Okay. So my first move is always going to be u times v. So I'll write this out. Let's see, what color did I write it in? I wrote it in blue, so I'll write it in blue. Okay, so my uv is just x e to the x. That's uv. Then I'm going to subtract the integral of v, which is e to the x, du, which is d to the x. Or not d to the x, dx, sorry. Okay, so there's my v du. V du. So when you do these problems, you should write out you should write all this out kind of off to the side. Or under, I don't care where you write it. Just, there should always be 4 lines over here. Maybe more, just because sometimes this will involve u substitution, but 4 parts so that you have the u, the du, the v, and the dv. Okay? So that's where we're at. Now we just have to integrate this, which is easy enough. And that's where the c comes in at the end. Okay? So there's still going to be a c. I mean, in theory, we could have put a c here if we wanted to, but it's just not necessary. Just got to have it at the end. Okay? Now, maybe you're thinking, why is this better than this? Well, if I'm given it as a definite integral, I can evaluate this. Okay. And so if I have this, I mean, this could be a curve, right? You could graph the line y equals x e to the x. And if we were looking for the area under the curve, we could do that with this integration. Okay. Moving on. Here's example 5. First, we got to make some trigonometry in there. And maybe you're thinking to yourself, wait a minute, there's only 2 things here. There's the arc sine dx. Can I just take the integral of that? The answer is no, you can't. You'll see. Okay, so we're going to make u the arc sine, and dv is going to be dx. Right? So it's not really that hard. But the fact is, we don't know. Was the integral? Did we learn the integral of the arc sine? We learned how to get the arc sine from integration, but we didn't learn the integral of the arc sine. We learned the other way. Okay? So we know how to find the derivative of the arc sine. What is this? Do you remember? 1 minus x squared. Good. And then this one's easy enough, right? Okay. So du equals 1 over the square root of 1 minus x squared dx. Got to have the dx. Okay. And then when I integrate both of these, you just get v equals x. Okay. So put it all together. Let's see what you get. All right. So, wait. Okay. So here's the setup. uv. Obviously, I put the x in front. Then v There's my v du. Okay? And you could have set this up differently. You could have said x times 1 over whatever. Okay, what am I going to have to do now? Yeah, I'm going to have to do u substitution with this x squared, or 1 minus x squared. Okay, so here it is. U equals 1 minus x squared. Du is negative 2x dx. Then I just bring the 2 over. So then I've got my x dx. I can replace that with this negative 1/2 du. Okay, and then this becomes u to the negative 1/2. Like so. Now notice I changed it to plus because this was negative, so that's why I changed it to plus. Threw the 1/2 out in front, so we don't have to worry about it right now. And it's just a matter of integrating this. So 2u to the 1/2. So there's my 2 from the fraction that was on the bottom. U to the 1/2, u is this. I could go one more step, did I? Of course. And there's your most simplified form of it. Yes, could you have stopped here? Yes, but you know me by now. Okay. And one of the things, again, I think that's important about a problem like this is maybe this will be built into a FRQ, but more than likely it'll be a multiple choice question. And so being able to choose, from an answer that maybe looks a little different than what you have is important. Now, ultimately, does this seem simpler than this? Of course it doesn't. But we can do something with this now, okay? We can use this now, depending on what the x value is. If you were to try to evaluate this, besides just punching it in a calculator, okay, fair enough, right? You'd have to graph it and then figure out the area under the curve and all that stuff. And so this allows us to do it with any particular x, okay? We're going to do one more example. Question? Last example. Okay, this one is a definite integral. And so here, we definitely have two parts. Okay, we have an x squared. We have an x squared, and then we have a natural log of x. So I want you to decide what you want to be what, and try to work through it, and see how it goes for you. And then I'll show you the way I did it. I want you to stop for a second. Okay, you all chose u to be x squared. I understand why. Okay. Okay. So what's happening as you get into what happens as you get into this problem, right? You have an extra x after you differentiate x squared, right? And so that x. So let me write this down for a second. Okay. Here, what I'm trying to show you is that here's where your flag should have come up. Okay. Du equals 2x dx. There is not an extra x here, right? It's one thing to have an extra constant, and then we can balance that out. But I don't have an extra x. This x is connected to the natural log. You can't think of it as, x dx like by itself. This is you have to think of it like this. It cannot be separated, okay? So you cannot sub in and put a du here without the natural log having some number there, okay? So this should have been your flag to go, this ain't gonna work. Because I got no place to put this x, and you can't throw a 1 over x out there to balance it out. That only works with constants. So it's at this point where you should have went, no, this is not gonna work. I picked the wrong u. And I totally understand. And I to be honest with you, I'm glad you all picked u to be x squared. Because one of the things you're gonna have to get used to is the idea that I gotta start over and try again, because it's not gonna always work.
Wait, what's the antiderivative of natural log x?
Natural log squared over 2. Yeah, right. So that doesn't get you anywhere either, right? So you're thinking there's the one, okay. So that's why once you get to this point and you realize I have an extra x that I can't resolve, that's when you should up. Okay? So your u should actually be the natural log of x. and x squared dx will be your dv. Now I'll finish. Okay, so du, of course, is 1 over x dx. When you integrate x squared, you get x to the third over 3. So that's kind of where we are, right? So yes, you have fractions. You're going to deal with fractions. It's fine. I was talking to my Algebra 2 about their test the other day. You know, I had to warn them before the test, you're going to get fractions, because they were so worried. You know, the first class I forgot to say that too, and they were freaking out that they were getting these crazy fractions, and it's okay. Fractions are okay. All right, so here we're at. UV, and of course you could write this a little differently if you wanted to. V du. Now, I chose to write it all out and not deal with the 1/3 yet, because this is going to cancel out here. Okay. Really got here. Still have my 1/3 x squared, and so that's where my 1/9 is going to come from, because this, of course, when I integrate this, I get this. We just did it over here. Okay, and so that's where my 1/9 is going to come from. So now I'm going to switch over to another screen because I've run out of room. So from here, I'm going to sub in the e in both, and I'm going to sub in the 1 in both, or not both, all three. Almost forgot about that one. Okay. So there's my substitution. This is just the same line from the previous page. Okay, so I've got e to the third over 3, natural log of e to the third over 9, minus 1/3, because 1 to the third is 3, natural log of 1, minus 1/9. And in theory, if this was an FRQ, which I don't know why it would be, but maybe it's part of one, you could be done here. There are no variables left, but we're not going to be done because practicing our natural log properties is fine. What is the natural log of e? 1. What is the natural log of 1? 0. Okay, so this is going to go away. This just basically goes away. And here's what I've got so far. This goes away, minus the minus 1/9, so that's plus. Okay. If I were to get a common denominator now, what would this change to? 3e cubed over 9. So I've got 3e cubed minus e cubed, which is 2e cubed plus 1. That is the simplest form of the answer that we can really get. You could keep it separate too and say 2e to the third over 9 plus 1/9. That is also the same thing.